All right, thank you for coming to my talk on learning wildfire spreading patterns through genetic programming. My name is Max Green, and I worked on this project with my friends Todd and Carl. The first thing that we're going to talk about is the growing cost of wildfires. Over the past 50 years, we've seen a steady rise in the total number of acres burned per year. 9 out of the past 14 years have resulted in record-breaking total number of acres burned. In 2018, we saw one of the most disastrous fires that has ever occurred in North America, known as the Camp Fire. This happened in the Sierras of California and resulted in over 18,000 damaged structures. It was deemed worse than the past 10 deadliest California fires combined, and it had a estimated $9.3 billion damage costs. In addition to sort of the monetary side of the damages, people, even if they aren't caught in this fire event, are really affected by it, both in the quality of air that people breathe and in the communities that are physically displaced by these events. And I witnessed sort of this firsthand as I was living in close proximity to the Camp Fire when it got out of control 2 summers ago. And so sort of that experience is one of the large motivations for this project. So the first question that we're going to ask is sort of how do people normally model wildfires? And, fire is a product of heat transfer from an energy source. And so that process can be modeled, by looking at radiation and convection, conduction of heat and materials, and advection. And so typically, these processes are coupled together to build fully physical models that are based on, the laws of chemistry, physics, and ecology. And these will take the form of, massive coupled sets of partial differential equations. And, these models are really great at predicting certain things and not so great at predicting others. And so sort of the other side of this is on the research end. In academia, we're seeing a large interest in applying reinforcement learning methods to take advantage of the sort of recent resolution gains in satellite images. And today we're going to talk about the potential for using evolutionary methods. So the roadmap for today's talk, our goal here is to reproduce the spreading patterns of simulated fires using a series of genetic programs. And so the first step in that is simply to simulate a fire. To do that, we're going to use an agent-based model. So that basically means that this simulation is going to occur in discrete time and space, and we're going to spread fire according to a known spreading function. Then we're going to use that data that's generated from the simulation to train a set of genetic programs and see whether or not we can recover that behavior. And we're going to use a regression known as symbolic regression. And the cool piece of this is that the output of a trained model is just an algebraic expression. And, potentially this can be interpreted. All right, so to start, we're going to look at how this agent-based model works. So agent-based models, as I said, work on discrete time and space, and so we're spreading fires over a grid. In this visual here, the site that is circled, site IJ, is being considered for ignition. So all of the red cells represent cells that are on fire, and all of the green cells represent potential flammable materials. And so right now, as site IJ is being considered for fire, it's going to look at the behavior of its neighbors. And we define the neighborhood of a cell as the von Neumann neighborhood, which is simply the 4 adjacent neighboring cells. And then the attributes of the neighborhood that we're looking at is the humidity, temperature, wind speed, wind direction, and elevation. And we're going to give the program a little bit of an assist and do some feature engineering to distill a little bit of the information encapsulated in these attributes. And so the first feature that we're going to talk about is an elevation feature and then a wind feature that's going to have some trigonometric functions in it. And then the temperature and humidity are simply going to be averaged over the neighborhood values. And so for our elevation feature, we're really just trying to make sure that fire always is going to have a higher likelihood of spreading uphill, right? Because heat rises. And so we're just looking at the sum of the exponentiated negative differences between a cell and its neighbors. And that is just going to lower the likelihood that fire spreads downhill. And this delta z term is just a vector of differences of heights. And then the wind feature is going to be really similar. We want to make sure that fire spreads in the direction of wind. And so we're going to sum over all of the cells that are currently on fire and then weigh the direction of wind, where the wind direction is in radians, and the sine and cosine factors just indicate which of the neighbors are currently on fire. To generate the synthetic landscapes, we're going to use a technique that's called Perlin noise that is actually from like the movie and entertainment industry. Each layer in the landscape is just a matrix of floating points. To generate these, we initially draw, n by n samples from a Gaussian distribution, and we want, ideally, in order for the landscapes to be realistic, we want the distribution to be pretty smooth. And so we're going to interpolate between neighboring sampled values iteratively using a quintic fade function. And so in this image, you can see different stages of interpolation. So starting at time 0, there's just a random noise distribution, and then at 24 it gets a little bit smoother, and then by the last time step at 99 you can see a realistic spatial distribution. It almost looks like rolling hills, which is exactly what we're looking for. The next piece of the model is the function that determines whether or not a site is going to ignite. And so in order to make the fire simulations before any type of learning happens, we're just going to use a naive balanced logistic model. This model's parameters were tuned heuristically just to produce visually realistic spreading patterns, one of which is exampled here. The black arrows represent the wind direction, their lengths represent the magnitude. And then you can see superimposed on the image is topographical gradient lines. So we'll see that fire is spreading from the center in the direction of wind and uphill. Here is a small simulation of a wildfire. The last piece is the actual evolutionary process that's happening. So after the data is generated, we are looking to reclaim that logistic function. And so we're going to start out by generating 100 or so random expression trees that are going to be used as a probability function in a simulation. Okay, and the expression trees can be comprised of a set of functions and a set of terminals, and we're allowing plus, minus, protected division, multiplication, cosine, sine, and some ephemeral constants to construct the trees. We're going to evolve this population using tournament selection of size 4. So basically, the individuals that are able to predict a simulated fire well are going to be allowed to reproduce with one another. And the fitness function that we're using is simply the intersection over the union of true and predicted sets. So to zoom back a little bit, let's quickly go over the general experiment flow. So a landscape is generated. We're going to use that Perlin noise algorithm, and then a fire is simulated over the landscape using the balanced logistic function. And then we're going to take the genetic program and attempt to recreate that spreading behavior by evolving functions through mutation, crossover, and selection. And so our desire here is to find solutions that do two things: produce accurate predictions at 2 timescales, at short and long-term intervals, and then are able to generalize across different environments, right? We don't want solutions to be overfit to a single environment. So we do that by looking at 2 different experimental designs. The first is going to be generalizing to landscapes. And so to do that, we train on 10 different landscapes and then test on an additional 10. And the best solutions, ideally are able to generalize to that design. We do this across 16 repetitions, allowing 50 generations for evolution, and choose a population of size 100. For the second experiment, in which we're looking at a finer temporal resolution, we're going to train and test across a single time step. So these individuals are going to ideally be really good at predicting how the fire spreads at the next time step, as opposed to how the fire spreads from the first to the last, with the hope that the best solutions are able to predict cells on fire just at the next time step. We're going to repeat this process 20 times with 100 generations and a population of size 100. We consider 3 different genetic models, the first being a null constant model with a single tunable parameter beta, the second being a logistic model, and this really represents the upper bound on the evolution process, because this model only has to tune the parameters that we determined in the underlying spreading function. And then the third model is a free-range algebraic expression. So it can be any tree, just has a max depth of 17. And this is really what we're interested in, and whether or not the free algebraic expression can, approach the accuracy of the logistic model. And so after some hyperparameter tuning, we come up with these crossover and mutation rates, and we can see that the fitness landscape is pretty rough, although there is some trending increased fitness, in certain regions, and so that's how we determine how to tune these hyperparameters. So then the question remaining is how well does this work? And so visually, some of these solutions perform really well. The yellow colored pixels represent the true spreading pattern, and the orange pixels represent the predicted spreading pattern. And you can see that this particular solution underpredicts a little bit, but is overall a pretty good fit. It's spreading in the right direction with relatively the correct rate. The way that we are going to quantify the results of this is by looking at some learning rates. So on these graphs, we're looking at the average fitness over 16 and 20 repetitions across both of the experiments, so the landscape generalization and then the temporal generalization. And we can see that in both cases, the genetic program nearly approaches the performance of the logistic program, which is really cool. And the constant model, as expected, does pretty terribly. We see the difference in scale across the y-axis for both models because it's just hard. It's a harder problem for the genetic program to generalize well to multiple landscapes than it is for it to, predict single neighbors that are going to catch on fire. The next way that we evaluate the models is by looking at how the fitness changes as each individual is being evaluated. So this is a similar plot, but at a finer temporal resolution. And interestingly enough, for the landscape generalization, we see that the genetic program is actually able to surpass the logistic function, which is really interesting. And, if we could carry this experiment out for longer, I would guess that they would both converge to the same fitness value. Alternatively, we see that the finer temporal generalization experiment, the GP model simply approaches the performance of the logistic function. So here we see some similar results. The only difference is that the red box presented is the true model, right? So this is the logistic function, but the parameters are already given, right? So nothing has to actually be learned. And this is the true upper bound for both experiments. And one thing that stands out in these plots is that in some cases, the testing fitness is higher than the training fitness. And this is one issue with the experimental design. There's a lot of variance in the landscapes that are being generated. So certain landscapes are just easier for the genetic program to learn than others. And we hypothesize that the testing landscapes just happen to be easier than the training landscapes. But overall, we're seeing the same trends that were expressed in the learning curves. The genetic program is typically doing a little bit worse, but comparable to the logistic function, and the constant program is, well, not doing well at all. So sort of our conclusions and next steps section, we were able to recover some of the behaviors of the simple synthetic fires, that spread according to the known spreading function that we defined. However, real fires are much more complex, right? They don't evolve based on a logistic function. We found that there's a lot of variability in the results of the model, and that there's a lot of heterogeneity in the solution form. So the same spreading pattern can result from lots of different functions, right? And so that makes it hard for the genetic program to actually find any causal relationships between the input features and the state prediction. Again, the GP could produce spreading pattern, but not the form of the underlying model. So our next steps are to take this method and try and reproduce a real fire, specifically the 2016 Fort McMurray fire that happened in Alberta, California. And then the next step is to introduce those two objectives as a multi-objective fitness function, so that individuals that are allowed to pass on to the next generation are really good at both generalizing across multiple time scales and different landscapes. Thank you so much for listening. I really want to hear any suggestions that you have. How can we improve these methods? Was anything unclear? And then, where do you think this research should go from here? We had a lot of fun working on this project, and we have a lot of ideas for how this can be improved and how we can use this model in different contexts. So we're really excited to hear what you have to think. Thank you.